Let's start. Thank you, Mikhail, for the introduction. So I'm going to present you today the results of the first stage of this international benchmark that we lead within the lab here in Ecole Centrale de Nantes in France. And glad to be here again at IBSim and talk about first of all, the motivation and objectives of this benchmark. Let me briefly tell you about them. Then our approach, since it's an image-based simulation, so we had to prepare the data, input data for the benchmark. And so I will share with you some interesting conclusions about the first microscale results from it. So just a little context before, for those of you who are not familiar with these fibrous materials as reinforcements of composites. Basically, in composite manufacturing processes, we have initially the textiles, which are the reinforcements. Then they are preformed within the put in the mold, injected with the resin. And then the cured part becomes like this at the end. So this flow model, flow process is guided by the Darcy's law, which you can see here, which relates the volume average flow velocity to the pressure drop. And here the key parameter is the permeability, actually here, which is a tensorial property. And so to introduce a little bit for those of you who don't know the fibrous materials, they are very specific class of porous media, which own the dual scale porosity, anisotropy, and variability. And the matter is that very few commercial software can compute permeability of porous media, and the majority of them are not designed to address such kind of class of multi-scale fibrous media. Few benchmarks in our domain have taken place in terms of the experimental measurements of permeability, and they revealed the high discrepancy of the results, at least 20%. You can see some references here. And moreover, the influence of material geometrical variability on these properties difficult, or at micro scale, it's even impossible to appreciate through the purely experimental effort. And that's why we organized this virtual permeability benchmark, which is the first contribution to the numerical prediction of this permeability of the real fibrous structure. So I give you, this is the advisory board. We lead this benchmark together with our colleagues, mainly from Kaiserslautern, IVW, and also with the support of colleagues from KU Leuven, from University of Delaware. And so the objective is develop general guidelines for the image-based numerical prediction of permeability of engineering textiles. So for that, we provide already segmented images of the material to eliminate possible sources of variation. This is a topic itself. I think we already discussed it a little bit last year, the segmentation process for these kind of complex structures. At this stage, we didn't pose any fixed conditions to participants, like methods, boundary conditions, or discretization, because we really wanted to have the general overview of the existing and employed techniques in the field. And also it will allow to see the influence of the variety of parameters on the results. And also, this is somehow related to the question of the computational resources, because even though nowadays we have quite powerful clusters, still for these kind of complex microstructures, they have to be really meshed in a refined way. So it means a lot of degrees of freedom and so high computational resources. And so without fixing the conditions, we actually do not limit to use different techniques, whether it's different discretization or 2D or 3D computation, or even subdivision into subdomains, because it's not only the question of the limited computational performance, but also the memory often. Together we had collected the results from 16 participants from 10 countries. You can see the list here. And the general approach was to take first the material from the which was used in the experimental benchmark. It's a woven fabric, and since it's a multi-scale material, we go from the microscale to the macro scale, because in the end, what is of interest for the manufacturing is the macro scale permeability tensor. Which will say how the part basically will be fulfilled, how the flow fronts will advance, and this defines the final quality of the part. So we start from the micro scale, which is at the scale of fibers. The fibers are themselves assembled in the yarns afterwards, and then they form their textile. So the first stage concerned the microscale, which means the single scale flow between the fibers. Then out of that, we obtain the intratoll permeability. And then we will be able to put it as an input for the mesoscale simulations afterwards to perform them at the scale of the textile. So here you have the flow within the yarns and between the yarns. So at the next stage, it will be multi-scale flow, and to arrive at the end at the permeability tensor, for which we have also the experimental values out from the experimental benchmark. So few words about the material itself. At the micro scale, what does it represent? It's actually each toe is composed of 3 yarns twisted together. It's very slight twist, 40 twists per meter, which means 1 twist every 25 millimeters. However, you will see afterwards it's not negligible actually for the permeability. And we saw that the fiber diameter varied. So it's a glass fiber woven fabric, which you can see here. We scanned a sample at the resolution of 0.2052 microns. And then what was provided to the participants is this subvolume, which was quite representative because we took the whole yarn thickness, tow thickness, and you can see there it contains around 400 fibers. So it's from one point of view, it's reasonable from the computational resources point of view, not too big. Not to limit certain participants to perform their calculations, and at the same time it's representative in terms of the variability of and the fiber distribution inside. So here you can see the segmented image we provided, so binary image with this size approximately, so it represents around 120 million voxels, and the averaged over the sample fiber volume fraction was 56%. Why am I talking about the fiber volume fraction? Because it's a very important parameter that influences the values of permeability, and we will back to it later. So here you can see the general overview of all the provided results. kx, ky, and kz. So basically two in-plane values, kx and ky, and through the thickness value, which is, of course, in plane, they are different because we are in the fiber direction and transverse to fiber direction. And so that's why we can see close values of kx and kz and much higher values of naturally ky, which is in the fiber direction. And so if we have a look at the coefficient of variation, actually it's without the analytical results, which are in crosses here, they are quite big. And we still can see that 81% is the smallest one for the fibers for the permeability values in the fiber direction here. So this is taken into account the obvious outliers that you can see here, the values that are very far. And we explained that why they are situated there. I will not go into details here, but basically whether their scaling was not respected or the structure was idealized compared to the real structure. So these coefficients take into account the presence of these outliers. So the purpose was to analyze different parameters and to probably eliminate the inconsistent results so that we can have a clearer maybe picture about the coefficient of variation of the results that are consistent, that correctly take into account all the factors. So this is the general overview of all the results, and among them I should mention there are 2D results, means that participants took the series of 2D cross sections along this sample and then calculated out of them the value for the whole 3D volume. And what was interesting is nobody from the participants used exactly the same methods and conditions, except for only two. So basically only two results had the same setup. And here you have an overview of all the variety of parameters that were varied. I won't go into the details of this, but what is important for the image-based calculation in general, you can see that in terms of the discretization, what can be used is whether voxel-based approach or geometry-based approach. And the second one was used particularly from very often from the computational resources point of view, because going from this amount of voxels that I showed you to the another geometry, when you take into account when you remesh your domain in order to reduce the number of elements, it was very often more interesting from the computational resources point of view. And then also you can see that it's 3D or 2D. As I said, due to the limitations of memory, sometimes it's much more interesting to perform a set of 2D calculations instead of the full 3D calculation. However, we had to see which price we have to pay for that, whether it's representative or not for this kind of structure. Then you can see that Stokes and Navier-Stokes flow model were used, but I should mention that, of course, Stokes is more than sufficient for this kind of problem, because we are in the regime of creeping flow for this kind of problems. And you can see that the techniques, finite volumes, finite elements, finite differences were used. And here, what was important for the particular image-based calculation is, of course, to see how the model was discretized, refined, and then it often ended up with the different fiber volume fraction, which came from this approximation local. So when we speak about the image-based calculation, what you can see is here is sometimes it can be interesting to subdivide your volume into a sequence of subvolumes, subdomains like this, and then to deduce by the renormalization technique the global value. So it's a series of arithmetic and harmonic means on the subvolumes afterwards. And that's what different participants did. And what was interesting for the results here, you can see that with the increase of number of subvolumes, naturally, and this is an expected result, we reduce the permeability value. So the same for the transverse permeability values here, you can observe with the exception of several values, but this is due to the use of not exactly the same technique. Because, for example, the result 8a, it was not a renormalization, but it was a Darcy simulation at macro scale. Macro means macro for this subvolume, for this sample, with the locally calculated permeability input before. So what showed this result is that if we use, for example, 10 subvolumes, it was only 15% deviation from the main cluster of the results. So this approach can be really interesting if we are limited in terms of the computational resources. But we have to pay attention, of course, to the number of the subvolumes. And also this technique, of course, allows to calculate only the main permeability tensor components, like here. If ever we have anisotropic effects, we will not be able to capture them on the scale of the whole volume by using this approach. So when we think about the image-based calculation, we should think about what is the representative elementary volume we have to address, because we can make calculation which is not representative at all. And that's why, for example, in this case, for this particular volume, one of the participants made an exercise to verify if ever the smaller domain can be used for the computation. However, what we can see on this graph, it was not the case. We didn't have any stagnation on the permeability calculated on the subvolume. So really the whole sample had to be taken to calculate the permeability. And also we have to keep in mind that some of the techniques allow to maybe preliminary estimate by the imaging techniques, such as texture analysis, for example, to estimate how big should be the volume taken within the sample so that it is really an RVE. So this can be made by some image processing techniques to see the stagnation of certain gray level characteristics to evaluate that. But that is only the information about the geometry of the structure. However, this stagnation can be different for the value, the property of interest that we want to evaluate. So at certain size, maybe the geometry will say, okay, this is our RVE, but in terms of the flow properties, the size of the RVE can be should be maybe bigger. So these are the things that we should keep in mind when we perform the image-based calculations. And also, what we saw for this sample is that the values in these two directions, they are both actually the transverse permeability values, which should be equal for this, because we know that the yarn is a transversely isotropic structure. However, that was not the case here, as the results showed, and the reason for that was that the dimension in the through thickness direction here is 1/8 of the in-plane dimensions. And so we saw that in the values of that influence on the values of the permeability, basically. So in the through thickness direction, we had not sufficient number of fibers, so this size was not statistically representative, basically. And this is also important to take into account. And also, when we compare these two directions, in plane and out of plane, we can see that the boundaries, so for thickness direction, they are much far from the imposed, the effect should be, is expected to be smaller. While they are quite close when we force the flow in the x direction here. And so that's what
excuse me, Elena, you have about 5 minutes?
Yes, thank you. So that brings us to the next point, is the influence of the boundary conditions. And that was interesting to see that when we compared the results of the same technique for periodic and symmetric boundary conditions, we had this dependence for Kx, while for Ky values, it was the opposite tendency. And for when we speak about the Kz, that I've just shown you that the out of plane value, the effect of boundaries was expected to be much smaller. This is the case because actually there's no trend like for Kx and Ky. And so when we have a look at the difference, you can see also that the difference is much smaller here between whether we apply this or that kind of boundary conditions. Of course, this is not the trend for all the structures in terms of how periodicity and symmetry correlate. This is particularly for this kind of structure here. But it was interesting to see the effect of the dimensions of the domain. Another important parameter, as I just said, is the fiber volume fraction. And so since we perform the calculation based on the image, it can vary from method to method because different model sizes are used, cropping of the edges some participants applied, and also the discretization of the domain. And what we knew for this particular sample is that, moreover, the fiber volume fraction varied along the fibers. And that's what we could see when one of the participants performed the exercise of calculating on these subvolumes. And so we have the usual decreasing trend of the permeability with respect to the increasing fiber volume fraction here. However, this is not the same what we could observe for the Kx and Kz values. You can see here that we do not observe the same trend on these subvolumes. And actually, this is the result of one of the participants, this one. However, if we have a look at another result, we can retrieve this trend for Kz and not for Kx. So that was the question for us. So we had a look more closely to these subvolumes that represented the variation of fiber volume fraction. And so here you can see the 2D results calculated on these subsections. And you can see that the KZ has this decreasing trend and not KX. And then when we add the results of the 3D, how they correlate, you can see that this trend can be retrieved by the both 2D and 3D, some of them. And what is particularly interesting is that for all the components, KZ and KY that I just mentioned, that we had the difficulty to see this decreasing trend, we actually found it in one of the results here, 16.6a. And this is decreasing result was because of the fact that the calculated technique was to calculate the full permeability tensor. That's what we found out actually. When we wanted to retrieve this trend, really the homogenization technique or volume averaging had to be used to calculate the full permeability tensor. So another interesting point to look at is the how the usage of the real image and the digital twin can be used, because sometimes we don't have access to the, for example, tomography, expensive facilities. And so sometimes the digital twin that already, the point that was discussed in some presentations yesterday, can be used. So this point was verified by one of the participants. It was generated by random sequential addition digital twin. However, it didn't represent the variability of fiber diameters and the twist that was present in the real sample. And that, of course, we saw in the permeability values. This is the, they were quite far. So it's still an open question how to correctly generate a digital twin for these kind of structures. So to conclude, we found out interesting results after the analysis of these microscopic results. First, we saw that we could have the reduced coefficient of variation by eliminating some inconsistent results, which is 14.25, which is pretty much like the experimental benchmark. The full permeability tensor is important to be calculated, and dominant effects were found by such parameters as permeability identification technique, the boundary conditions used in the tangential directions, and number of subdomains used in the technique. And as it comes to the boundary conditions, it's particularly the no slip and symmetric boundary conditions. They are not really convenient because they block the cross flows that can be eventually present in such kind of structures. And so for the image-based calculation, a good approach can be, like I said, subdivision into subvolumes. However, we should pay attention to the number of them. And of course, if the transverse anisotropy effects are present, it's not convenient as an approach. Concerning the 2D, 3D solutions, we cannot really conclude at this stage, at least for these particular results, whether 2D can be representative of the 3D. More investigation is needed. And for those of you who are interested in having a look at such microstructure, we made it available. And you can find a link on the IBSim website as well in the resources section for that. And the results will be published soon in this paper. And a few words about our, so we try to take into account all the conclusions from this first stage of the benchmark, and we implemented it in our in-house code. A few words about it. So it's Stokes Brinkman solver. Pseudo compressibility formulation is used because it allows to reduce the number of degrees of freedom. Only the velocity field is resolved, and it uses the homogenization technique. And so its name is porous, and it allows to calculate out of the real images or digital twin, as you can see here. And this is the example from the this benchmark. You can see the complex flow field that we can obtain through this kind of microstructure. So thank you for your attention, and actually concerning the way forward, we are currently running a second stage of this virtual permeability benchmark. And I know that some of the IBSim participants now in the audience participate in this second stage. And it's an ongoing stage until December 31st. So if ever anybody else is interested, you can still join us. Thank you.
Thank you very much, Elena.